Hi everyone, we'll be starting class in 1 minute's time. Alright, good afternoon everyone, and today's lectures are basically going to focus on us finishing up the Z-transform and how we can actually use it with respect to different equations and how to obtain a discrete time solution for such equations. Also, we'll be looking at the two possible forms of solutions that can exist, which I refer to as the infinite or open form solution and the finite or closed form solution in particular. So when we go through today's lectures and the material associated with those, we'll see in particular how these two solutions differ, but at the same time, how they can be similar in nature. So what we observed from yesterday's lecture is that the Z-transform is quite similar to the Fourier transform since it's based off of it, and because of that, by extension, it also shares a lot of similarities with the Laplace transform. In particular, the properties that we'll be focusing on in today's lecture will be the shifting property and the convolution property as well. But we won't be going too much in discussion for the convolution property. We were looking at the shifting property a lot more regarding everything for this lecture in particular. The convolution property is the same as the Laplace transform, that if you have a convolution in the discrete time domain, it's just a multiplication in the Z domain. And if you have a convolution in the Z domain, it's a multiplication in the discrete time domain as well. So it shares the same property for convolution regarding the Laplace transform. The shifting property, which is going to be the main property that we're going to be focusing on today, is going to indicate to us how do we go about solving our difference equations as of such. So this shifting property that we're seeing here, we're going to discuss this in a little more detail in this lecture, and then we will apply it in the next lecture that we're doing to see how do we actually apply this property and how do we obtain a relevant Z transform equation for our difference equations that are represented in discrete time. So the first property we're looking at is when we have our x of kt signal, which will be our discretized time signal, which is shifted by some nt factor here, meaning that this is shifted by a number of intervals of the periodic time associated with this discrete time signal. This discrete time signal that is shifted is also multiplied by the unit step, which is shifted by the same interval. And that what we're going to observe here is how do we obtain this mapping of z to the minus n x of z. The second property is when we're going to observe just the x of kt signal being shifted by nt intervals. And how do we obtain this expansion here for this shift accordingly, depending on the value of n. So let's observe the first property in particular. So if we let that entire shift of x and u here equal to y of kt minus nt representing that same interval shift, and we apply it to the Z-transform equation that we saw in yesterday's lecture, and we expand out this power series, what we can see how what this looks like is basically if we have our x of kt by u of kt signal here, where our x of kt signal is represented by these red stems and the u of kt signal is represented by the blue stems, when we shift these accordingly, when we do this multiplication, everything that was on the left-hand side here will be multiplied by 0 because of the nature of the unit step in discretized time. So everything before k equals 0 will just disappear and become 0. And everything from k equals 0 going onward will maintain the same values as of such. When we shift both signals by a factor of nt, and this being minus nt, so this is going to be a shift towards the right. Depending on the factor of n here, that means our x of kt signal now shifts by that n factor that represents this nt here. Similarly, when we have our u of kt minus nt here, that's also a similar shift regarding that shift that we just now had with the nt factor. As of such, when we multiply the two signals, and both of them are delayed by the same factor nt, it comes like if we just took this original signal here and we shift its contents by nt itself. So if we watch this mathematically for our expansion with the Z-transform, and let's change the index of the summation here so that m equals to k minus n. So if we rearrange this and make k the subject of the formula, we can get m equals to the negative n and so forth. And when we do this, and we change this here, so our representations for x of m and u of m and so forth, and we conduct our mathematical evaluation of the Z-transform, we see that when we expand this out accordingly with our powers of m and n, it comes that such that we have the z of the n formula here being, with the summation series being x of n z to the minus n. And this x of m z to the minus n, when we started out, if we say x of n here z to the minus m by itself, it's just going to be our x of z formula to begin with. So that's how we get the mapping mathematically to form this proof as of such, for the shift of the x of kt signal and the u of kt signal by the same factor of nt here. In observing the second property, which is known as our shifting property, this is when we start dealing with a non-causal signal, because we multiply by a unit step in the first property, we were only dealing with causal signals, being that the index of k was 0, and for everything of the index of k being less than 0 is just going to be an entire 0 signal. For everything for the index of k being 0 and onwards going towards positive infinity, the signal existed. But once we don't have that unit step, we just have x of kt, and then we're going to be shifting this by any interval of nt, we'll now be dealing with a non-causal signal. And we're going to observe what happens when we delay this x of kt signal by one sample, being minus t, as well as two samples, being minus 2t. So we want to watch first, how do we delay the signal by one sample, and what the relevant Z-transform for this signal is going to look like. So we have our x of kt signal here, and we can see, just for illustration purposes, when we have the x of minus 1, we can go ahead watching this in particular for observation. Okay, so before I proceed with this, let's go back the last step in the first property. When we do the substitution here, where we let m equals to k minus n, this here, where we have in our brackets being kt minus nt, we can factor out the t factor, so we get k minus n here, so this becomes x of m t. And because we deal with t regardless, we can just ignore the t here for our explanations. So it makes our life a lot more simpler when we're actually doing the factorization here for our equation. Similarly with u of kt minus nt, if we factor out this t factor here, it goes to become k minus n, which represents our m here as of such. So we get u of m. And then we have z of minus k here. So if z of minus k, we make k the subject of the formula for this equation, we'll get minus k equals to minus in brackets m plus n accordingly as of such. And for this summation series part here, we have k equals to 0. We just substitute k equals 0 here as of such, so this becomes m equals to negative n as of such regarding this. So because we multiply by this unit step here, being u of m, that means instead of starting at m equals to negative n, the signal exists from m equals 0 go towards positive infinity. So this U of M signal just transfers to the summation series here to give us M equals 0 for the summation series as such. So because we now have the simplified summation series here without the unit step, because we factor in that unit step here for the summation series here, and when we expand this out accordingly, so this is going to be z to the minus n multiplied by z to the minus n, as because this minus sign is in brackets on the outside here. We factorize out the z to the minus n accordingly, and we have x of m z to the minus m with respect to m equals 0 to positive infinity. And this summation series here, it's similar to the summation series that we saw for the regular Z transform for x of kt. So because it's in regards to m here, and if we substitute this back so we get this back in terms of z, it now becomes z to the minus n here of x of z. Because this summation series is of the form of x of kt transform into x of z. That of such, because we have this mapping, we just show the mathematical proof for when the x of kt signal is multiplied by the u of kt signal and both are shifted by a factor of nt. We obtain the mapping here to show that the shift of these two signals by the nt factor in the Z transform version is going to be z to the minus n of x of z. So this is just basically the mathematical proof as to how the property exists. And just to emphasize this, you will not be tested on proofs. You will only be tested on application of the properties and transforms themselves. Right. So let's get on to the second property in particular, when we have only the x of kt signal that's going to be shifted by one sample or two sample accordingly. So when the signal is delayed by one sample, this is going to be x of kt minus t. And if it's delayed by two samples, the signal now becomes x of kt minus 2t accordingly. So we want to observe for the first effect what's going to be the signal when it's x of kt minus t, meaning that it's delayed by one sample. And because we don't longer have the unit step being multiplied here, this x of kt signal can be a non-causal signal in particular. So we're going to have to observe what happens when we actually do this and we start delaying the signal by a set number of samples. So if we start with our generic x of kt signal here, represented by the stem plots for each sample that is taken for every kt interval. So we would need to observe here that because we're delaying the signal by one sample, we need to watch this x of minus 1 value in particular. So we have our x of kt signal here represented by our graph. And if we did the x of z transform, we know that because we're doing the one-sided z transform, the x of z just only maps to only the positive part of this graph here, meaning that we only be observing from x naught go all the way up to x to the n or x to infinity. However, when we delay the signal by one sample, that means we shift this entire signal to the right by one sample. So this x of minus 1 value that existed on the negative side of the axis now becomes the x of 0 on our new x of kt minus t signal as of such, because of the shift. And when we conduct the Z transform here, we realize that, okay, we had x of z here when we had x of naught here going to x of some infinite value. But when we do the shift accordingly, and now we have this x of minus 1, we need to factor this in accordingly. So when we do this shift, the original contents here of x of z is now delayed by a factor of z to the minus 1. And that factor is multiplied by x of z here to maintain the same contents that were shifted. But because the Z transform is the one-sided Z transform and it starts at the 0 component here, we now have to factor in this x of minus 1 because of this kt minus t shift. So in factoring that, we say that the equation here is going to be our delayed x of z signal that we began with. So it's going to be z to the minus 1 x of z here in particular. And we need to add our new signal that is shifted onto the 0 point as of such in the graph. So this is going to be z to the 0 because we're at 0 here of x to the minus 1 value because of this x of kt minus t shift. So as of such, when you have a delay of an x of kt signal by one sample being minus t, the relevant Z transform for this is going to be Z to the minus 1 of x of Z plus x of negative 1, where x of negative 1 here will be the instantaneous value that was associated with it. Now let's observe what happens if we delay the signal by 2 samples now, and what's going to be the relevant Z transform for this difference equation as of such. So because we're delayed by 2 samples in this case, that means we need to observe the x of minus 1 value and the x of minus 2 value that's going to be associated with our shift, because these values here being on the negative side of the axis are now going to go towards the positive side of the axis when we do shift the signal accordingly by 2 samples. Recall that if we just did our Z transform on this x of kt signal, because it's the one-sided Z transform, that's going to be only concerned with the k equals 0 index going towards positive infinity. So we only concern ourselves with the positive values here. And this is going to represent our x of Z signal for x of kt. So yes, Z to the negative 1, the minus 1 represents the shift in the Z transform. So we see here that for x of kt, if we just did the Z transform, and this being the one-sided Z transform, we don't care about the negative values of Z, so we only concern ourselves with the positive values of Z here from k equals 0 go forward. And as such, this right-hand side of the signal here is going to be our x of Z. However, when we do our shifts by 2 samples here being minus 2t, we see that the x to the minus 2 and x to the minus 1 signals now form the part of the positive axis as of such. So instead of these being on the negative side of the axis, this is now on the positive side of the t-axis as of such. And that means we need to factor in this x to the negative 1 and x to the negative 2 values here for our Z transform. Now we saw here that in this part of the signal, which was x of Z, this still is represented by our x of Z signal, but it's delayed by 2 samples. So in the Z transform, this delay is represented by Z to the minus 2, where this minus 2 represents this minus 2t as of such. So the contents of the signal here becomes Z to the minus 2 x of Z. But now we have to factor in this x to the minus 1 and x to the minus 2. So this x to the minus 1 value here, when we factor this in, this is also delayed by 1 sample. And this delay of 1 sample means that it's going to be Z to the minus 1 representing the delay of x to the minus 1. And because x to the minus 2 is at the 0 index here, this is going to be Z to the 0 of x to the minus 2. So as of such, when we have a delay of 2 samples for x of kt minus 2t, the relevant Z transform for this difference equation here is going to be Z to the minus 2 of x of Z plus Z to the minus 1 of x of negative 1 plus x of negative 2 as of such. And in general, because we can see that the trend emerges from the delay of 1 sample to the delay of 2 samples, for any amount of samples represented by n here, capital N, we can do an expansion here accordingly represented by this relationship to obtain the amount. So for example, if we had the following difference equation here, being x of kt minus 3t, the relevant Z transform for this difference equation will be Z to the negative 3 x of Z plus Z to the negative 2 of x of minus 1 plus Z to the negative 1 of x minus 2 plus x minus 3. And we can basically obtain that expansion from just watching the equation right here above and just substituting the value of capital N to obtain our expansion accordingly for each one of these. So these properties that you're observing here in particular, being the first property and the second property here, these actually form the basis of how you go about solving different equations and getting them into the Z transform and the Z plane. And then we'll be watching in particular how do we solve those in the Z transform plane, as well as how do we inverse Z transform these to get back your discretized time solution in particular. So these two properties are very important as to how we go about solving these different equations. So make sure that if you don't understand anything at this point in time, make sure you ask your questions now. I'm giving you some time to ask anything that you're not sure about, that you're unclear about, because moving forward we will be using these two properties in particular. So ask your questions now. All right, doesn't seem like we have any questions regarding this. So at this point, let's move on. And once we hit the last lecture, when we start applying this, hopefully you guys can see how the application of these properties go about with regards to solving our Z transforms. So the different equations that we're going to be exposed with when we're watching discretized times, they can be mapped to something referred to as a linear constant coefficient difference equation, also known as the LCCD equation. And this basically represents the summation series here for us obtaining the LCCD equation as of such regarding this kind of mapping for the input sequence X event to an output sequence Y event. And if we let n equal 1 and n equal m here, that means n equals to m equals to 1. That means that we'll have y of kt plus t here in our brackets. I'll write this on the slide. So this here becomes y of kt plus t. This summation series here, because it's going to be I equals 0 and this will be n minus 1 here, so that's going to go just down to 1 minus 1 being 0. This here will just become a naught of y kt, and this here, because m is equal to 1 and we start at I equals 0, this will become b naught x of kt plus b. Oops, what I did there. So okay, clearly I'm gonna have to write this over. So this here was y of kt plus c. This here becomes b naught y of kt, and this here becomes b naught x of kt plus b1 x of kt plus t. And if we Z transform this accordingly, what we need to do is that because all these signals here positive t, we delay all the signals once by an instance of t accordingly. So this kt plus t here becomes kt. Everything that was kt now becomes kt minus t. And as of such, the reason why this delay is possible because we're dealing with linear time invariant systems. And in applying the shifting property here to these signals that we just now delayed by an instance of t, knowing that we only have to cater for when we have a delay of one sample, we can map our transform from the difference equation here accordingly using this property of x of kt minus t as of such that we just now observed. So y of kt here becomes y of z. A naught being a constant factor remains on the outside. Y of kt minus t becomes z to the minus 1 of y of z plus y of minus t, because this is a y signal here. And the b naught here is also a constant, so this remains as of such. X of kt minus t, we just substitute in z of negative 1, x of z here, plus x of minus t for this part. b1 being a constant remains as is, and x of kt just transforms to x of z as of such. If we assume that our x of kt signal was causal, that means for any instance of x being a negative value, that's going to be 0. The equation itself can be simplified and rearranged into a very familiar form that you saw when we were doing stability and the analysis of our first order differential equations. So the difference equation, when you actually do all this and you remap it and rearrange it as of such, gives you this first order form that we just now observed, where y of z here gives us the output response, the y of minus t here will give us our initial condition response, and the x of z part here will give us our input response as of such. Right. So that basically brings us to the end of the second Z-transform lecture. And the important parts to know with this lecture in particular would be that you need to remember those two properties that we just saw observed. In particular being the x of kt signal multiplied by the u of kt signal when both of these are shifted by a factor of nt, as well as the x of kt signal alone by itself being shifted by a factor of nt. And because those are different equations in the discrete time domain, we saw the relevant Z transforms of these in the Z domain as of such in this lecture. So it is important that you remember these Z transforms that's for each one of these properties, because those are quite important, in particular for when you're solving discrete time equations and difference equations in particular, as to how do we obtain our solutions regarding these. What I can tell you at this point is that the LCCD equation that you just now saw will not be tested. We will only be watching on the properties of the Z transform and how they can be applied to solving difference equations in particular. That is what's going to be evaluated and tested on your final exam. So before we move on to the last lecture, are there any questions regarding the material of this lecture? Because if you don't understand anything about those first two properties, when we move on to the next lecture, it's going to be a lot of problems if you did not understand what was done here. So if you really did not understand anything, please indicate so now, and I'll go back through it and try to make sure that you do understand and clarify whatever it is that you have misconceptions on. So please ask your questions now if there are any. It doesn't seem like we have any questions, so let's move on to the last lecture, which we're going to be dealing with regarding the Z-transform. Right. Okay, so this final lecture that we're going to be doing here, which is entitled Z-transform trees, is going to focus on how do we apply those properties that we just saw in Z-transform 2. And when these properties are applied to an actual difference equation that you may encounter when dealing with discretized time systems, how do we obtain the relevant Z-transform for these, and then how do we go about manipulating the Z-transform accordingly and get to the inverse Z-transform representation of it to get the discretized time solution for that difference equation. And what you're going to observe in this lecture in particular is that once you have your difference equation in the Z-transform representation of it, it's basically the same steps that you take when you're solving for the Laplace transform. You basically perform partial fractions, and once you have each of the partial fractions associated and solve for the constants and so forth, it's just basically a matter of looking at the Z-transform table to get the inverse Z-transform accordingly as of such. So we need to recap a little bit at this point. So when we're dealing with continuous time systems, we had an x of t signal here being our input, going into our system here being h of t, and this produces a y of t signal. And what this occurs in time is that the y of t signal here is a convolution of the x of t and h of t signals. However, when we have a discrete time system model, what happens in reality is that we will start off with a continuous time signal, being x of t. This x of t signal is sampled to form our discretized time signal x of n, and then this x of n signal here is subjected to the discrete time signal system h of n, which produces our y of n signal here. And because this y of n signal is still in discretized time, if we require for it to get back into continuous time, that requires us first to reconstruct the signal for a discretized time signal here. So when you're doing signal reconstruction, you basically get an approximate version of what the y of t signal should be because of this reconstruction process here. So because that you did this sampling process here to move from continuous time to discretized time, when you're going back to from discretized time to continuous time and you do this signal reconstruction process, this is an approximation process, and as of such you don't get the same signal being y of t. That's why it's represented by y hat here of t, because it's an approximate signal of the actual y of t signal if you did this in continuous time only. So any discretized time system in particular can be any sort of digital system that you may encounter, being like your registers, your FPGAs, microprocessors, anything related hardware and software wise. That is a good example of a discretized time system. Because we're still dealing with respect to discretized time, to produce our y of n signal here, also known as y of nt, it's also a convolution of the x of t signal, the x of nt signal, sorry, with the h of nt signal. And this is true because we're still in the time domain regardless. So the convolution holds true rather if you're in continuous time or discretized time. Now, if we have our difference equation here of this form that we just now observed in the last lecture, and we Z-transformed it, or the initial conditions were 0 and the input being causal, we basically obtain an equation here from doing all these mappings and substitutions in the form of y of z plus a naught z to the minus 1 y of z being equivalent to b naught z to the negative 1 of x of z plus b1 x of z as of such. And because we have this mapping here, and we also have that the initial conditions are 0 and the input is causal, this allows us to do the Z-transform immediately from just observation. Because y of kt here will just become y of z. the y of kt minus t signal here, because we no longer cater for the constant being the x of -1 or the y of -1 here. When we do a z transform, this just transforms to y of z, and similarly, this will also transform here to x of z as a sum. And this is done using the shifting property, but also that we assume all the initial conditions were 0 and the input signal was causal in nature. Right. So now let's actually look as how can we apply this in particular to an actual difference equation. So I'm going to show you guys right here on the slide how do we transform this into the Z transform. And then for your homework, after I do the initial transform here, I want you guys to substitute the initial conditions and then try to solve for a representation of the Z transform equation for y of z. And afterwards, when we go through the lecture, you want to see, okay, it's possible to perform partial fractions on this and then obtain the relevant inverse Z transform representation back into discretized time as of such. So if we Z transform this equation here, this y of kt signal will become y of z. The minus 0.1 is a constant, so that remains as is. The y of kt minus t signal here will become z of -1, y of z, plus y of minus t. This minus 0.02 is also a constant. The y of kt minus 2t signal here will become z to the minus 2. Oops, wrong. Z to the minus 2, y of z, plus z to the minus 1. Oops, something's going on with my stylus here. Give me a second. Right, z to the minus 1, y of minus t, plus y of minus 2t, being equal to 2 x of z minus, I made this being a minus here, in brackets, z to the minus 1 of x of z plus x of minus t. So we basically close our bracket there as of such. So we have our initial conditions here being y of minus t equal to -10, which we can substitute in here accordingly. And we also have a y of minus 2t here being 20, which we can substitute in here accordingly as of such. And we also have x of nt here being u of nt. So because x of nt here is u of nt in particular, that means that once we know this being u of nt being our discretized unit step, u of nt is characterized such that it's 1 for n being more than or equal to 0 and 0 for n less than 0. So as such, we have u of minus t, which is similar to x of minus t. From our definition here, that's just going to be 0. So everything that was x of minus t just becomes 0 as of such. The next thing to pay attention to, because this is x of nt equal to u of nt, on the ZTransform property table, which you'll be provided with, this u of nt has a u of z transform on that ZTransform table. And in particular, I'm going to look for this ZTransform table now to show you guys what it actually is. In particular, you can see here this u of nt, when you Z-transform it, it's going to be 1 divided by 1 minus z to the -1. So there's going to be 1, there's going to be 1 divided by 1 minus z to the minus 1 as of such. So everywhere you have x of z, because this was basically x of at. So everywhere you had x of z, that's going to transform to our u of z equation as of such, because x of z here was basically u of z accordingly. So when you do those substitutions as of such, and you perform your work in for this homework, you can see that the final answer will be of the form that's provided here on the slide. So you can verify that you obtain this final answer after you do all those substitutions and manipulations for x of z, y of minus t, and y of minus 2t accordingly in that equation. It's also possible for you to factorize this denominator here, because it's of the z to the minus 3 power. And I understand that some people do have trouble dealing with negative powers. So the simple way to go about this is just saying that x here equal to z to the minus 1. It implies that it is x squared, this will be z to the minus 2, and x cubed will just be z to the minus 3. So as of such, when you transform this, I'm just going to show you guys the denominator in particular. This will just become 1 minus 1.1 x plus 0.08 x squared plus 0.02 x cubed. And like I said, because some people have trouble dealing with negative powers of z because it's a visual conception thing, you can just do the substitution as of such, and then you can actually factorize the equation and then just put back in the z components afterwards to get back in terms of z. So it becomes possible, once you have your equation here in particular, to factorize the denominator, and once you have factors of the denominator here, you can then perform partial fractions and then use the ZTransform table to get the inverse. But we're going to be watching that in a little bit throughout this lecture, how we go about doing the partial fractions, and how do we go about doing the inverse transform to get the actual solution that required. Similarly, if you don't want to deal with negative powers of z, you can transform these into positive powers of z accordingly. And in order to do this, that means you multiply the numerator and denominator here by z to the negative, sorry, by z cubed. So if you want to transform this to positive powers of z, you just multiply the numerator here by z cubed and the denominator here by z cubed in order to do the transform to get into the positive powers of z. It's also possible for you to factorize the numerator as well. If they ask you to express the answer in pole zero form, as such, all the zeros will be the factors on the numerator, and all the poles will be the factors on the denominator as of such. So each one of these forms that we just sort of observed here, where representing y of z, is basically the same equation, just represented in different forms. It's just conveyed the same information. They just are different forms accordingly regarding these. So now that we actually transform that difference equation into its relevant Z-transform representation, the question now asks is what's going to be our output sequence for y of nt. To do this, we need to perform the inverse Z-transform. Now, there are three ways we can actually do this. Long division, which is going to be our infinite form. Complex integration, which we will never do, basically because it's very long in nature. And partial fractions and transform tables, referred to as our finite form. The infinite form is also referred to as the open form. Finite form is also referred to as the closed form. We'll be watching each one of these three ways in particular. We'll discuss about the long division and the partial fractions in a little bit of detail. We'll just briefly touch about complex integration because, like I said, we're not going to be doing this. We'll just show you guys what's the method for doing this, and if you ever have to encounter it, that's the method that you will have to use. So, for the long division process being the open form or infinite response, you need to divide the numerator by the denominator up to a certain power of z. And at this point, I'm going to actually have to do this on the whiteboard to show you guys how to do the long division for this. So, keep my ink here and pull up my whiteboard. So keep in mind, because that we're dividing here by this denominator, when we set up our long division table in particular to perform this long division, this is going to be on the left hand side and the numerator is going to be on the right hand side. So let's set up that equation in particular for our long division. So this comes like we'll have 1 minus 1.1 z to the minus 1 plus 0.08 z to the minus 2 plus 0.02 z to the minus 3 and we have a numerator here being 1.4 minus 0.6 z to the minus 1 plus 0.2 z to the minus 2. This is actually how do we go about setting up our long division process here for the open form or infinite response. And in performing the long division, we take the first factor here of the numerator and we divide that by the first factor here of the denominator as of such. So this 1.4 here is going to be divided by 1, which is going to give us a factor here of 1.4 for our quotients being our result. This 1.4 here on the numerator needs to multiply each one of these factors on the denominator to represent our remainder that we're going to be calculating for. This 1.4 here multiplied by 1 is going to give us 0.4. 1.4 here is going to be multiplied by negative 1.1, so I'm going to need my calculator here to solve for this. So it's going to give us negative 1.54 to the negative 1. 1.4 here is going to multiply by, so 1.4 here is going to be multiplied by 0.08 here, and this being z to the negative 2. So let's calculate that out. So that's 1.4 by 0.08. That's going to give us 0.112. And then we have 1.4 here being multiplied by 0.02 z to the minus 3. That's going to be 1.4 by 0.02 gives us 0.028. We then minus these two parts here for long division. So 1.4 minus 1.4 will just give us 0. We have negative 0.6 here. This is going to be minus 1.54. So it's going to be negative 0.6 plus 1.54. So minus 0.6 plus 1.54 is going to give us 0.94. And this is z to the minus 1. We have 0.2 here, minus positive 0.112 for z to the minus 2 factors. So this becomes 0.2 minus 1, 0.112. Which gives us a result of positive 0.112. 0.088 z to the minus 2. And we have no z to the negative 3 factor here, so that's going to be 0 z to the negative 3 minus positive 0.028 z to the negative 3, which will just be minus 0.028 z to the minus 3. The next step for the long division is that we want to be watching our remainder here, which we just now calculated for, and we want to divide this remainder here, the first factor of this remainder here, by the first factor of our original denominator. So that's going to be 0.94 z to the minus 1 divided by 1, be positive 0.94 z to the minus 1. And then we perform the same steps that we just now did, where we take 0.94 z to the negative 1 and we multiply by each one of these factors here in the denominator, and we minus it accordingly as of such. So this becomes 0.94 z to the minus 1. And I'm just moving this across because I want to need a little more space. 94 multiplied by 1 minus 1.034 z to the negative 2. And the reason why this is z to the negative 2, this is z to the negative 1 multiplied by z to the negative 1, gives us z to the negative 2. And then we multiply each one of these factors here, so 0.94 by negative 1.1, giving us that result of minus 1.034 z to the negative 2. And similarly, 0.94 multiplied by 0.08 going to give us 0.00752 z to the minus 3 plus we have 0.94 multiplied by 0.02, 0.0188 z to the minus 4. We have to minus these, so the z to the negative 1 here will just cancel, and we have 0.088 minus 1.034. So that becomes a positive, so that's 0.088 plus 1.034, give us a result of 1.122 to the minus 2. And we perform the operations as of such throughout, if we're just doing a long division process. 0.028, it's being in minus. So negative 0.08 minus 0.00752 minus 0.03552 z to the minus 3 minus 0.0188 z to the minus 4. So typically, what happens in our long division questions is that they tell you obtain the quotient or the solution up to a certain power of z. So in this case, if they ask for the solution being up to z to the minus 2, the last step for what we're going to be doing here is we're going to focus on this 1.122 value here, z to the minus 2 being divided by 1. So it's going to be plus 1.122 z to the minus 2. And basically stop here for our long division, being our end result. And we can verify this here, seeing that this was the answer that we just now calculated for when we did the long division. So when a question like this comes for long division, being that they ask you to find the open form or infinite response of a z equation, you're going to have to do those long division steps. And basically the question will tell you, get your result or get your answer up to the z to the minus 2 factor or the z to the minus 3 factors of such, so you'll know where to stop your long division. Because this being a long division process and is referred to as the open form or infinite response, the long division basically keeps on going towards forever, so you need to stop at some z to the negative factor when you're doing this division as of such. Once you have your z equation result here, up to some z to the minus factor, it's quite easy to actually apply the shifting property of the z transform to get this into the discretized form. Because this here just basically represents a sequence of values, because this is basically an infinite sequence. So this 1.4 here being a constant from the z domain into the nt domain, this just becomes 1.4 delta of nt. 0.94, because it's z to the minus 1 representing a delay of 1, that's going to be delta of n minus 1t as of such. And we just have the 0.94 being our constant. Similarly, because it's z to the minus 2, this delay in the discretized time domain is going to be delta of n minus 2t, and the constant which basically transfers across as of such. And like I said, because this is an infinite sequence, it's basically just going to be a vector of values if you actually have to plot this accordingly for each one of the instances of t. So in doing the long division process, it directly gives you the sequence of values which can produce the transfer function, and you can just do a very simple Z transform regarding this. Most of the time, the sequence will not end, given it to the form that we refer to as the open form or the infinite response of the equation. But if for some reason the sequence does end, or you convert to some value, meaning that when you're doing the long division, your remainder becomes 0, that means you have obtained a finite response for the equation. And you can basically do the same Z transform that we just saw here for the long division process and obtain your answer. But instead of it being an infinite response, it is going to be referred to as a finite response because you obtain the remainder of 0 during the long division process. Complex integration, which we are never going to do, is given by this fancy equation here, which is represented by a contour integral. And the evaluation technique for this is known as the method of residues. If you're more interested in this, you can do a little more research as to how this is actually conducted. But for the purpose of this course, we will not be doing complex integration. Partial fractions is the preferred form that we're doing when you're trying to solve for this equation and they ask you for the closed form or finite response in particular. And because we're doing partial fractions, it's basically the same thing as if we were doing the Laplace transform. It's the same technique that we'll be doing, as well as we're just going to have to pay attention to what transforms to look at on the Z transform table to do the inverse and obtain the discretized time solution as required. So the Z equation, before you actually start doing this, it needs to be of a proper form, where the degree of the numerator must be less than the degree of the denominator. If the form of the equation does not satisfy this condition, you need to long divide the entire equation until you get the remainder that satisfies this condition, and then you can perform partial fractions on the remainder. Alright, sorry about that. So yes, if you cannot satisfy this condition, you need to long divide until the remainder actually satisfies this condition, and then you can perform partial fractions on the remainder. Because the remainder here will just become the remainder divided by the denominator as of such. So if you had an instance like this, you'll get your quotient here being the value that we just saw on top of the long division table, plus the remainder which was the value at the bottom of the long division table, divided by your denominator as of such. And then you can do partial fractions on this part here. to proceed. Once you satisfy the condition that the remainder, the degree of the remainder is less than the degree of the denominator that you started with. So let's go back to our original equation that we just now had, where we had the factorized form of it. If we treat the z to the negative 1 here as our variable, it becomes to express this equation here into partial fractions as of such, where we can solve for the constant values of a, b, and c by substituting values of z to the minus 1 accordingly and solving for them, similar to what we did for the partial fractions when you're dealing with the Laplace transform. So if you're solving for a, b, and c, and you're using the same technique that I showed you guys quite a long time ago, and at the start of the semester, for evaluating partial fractions, you basically see that it's possible for us to solve for a, b, and c using that method that we observed in particular. So I'm going to actually just talk about one of these because the method is just going to be the same. For our a here, this is going to be 1 to, this is the factor here represented by a is 1 minus z to the negative 1. The numerator here remains the same when we're trying to solve for this. So in solving for a, the numerator here remains the same, and we'll put all factors on the denominator that are not associated with a. That's going to be 1 minus 0.2 z to the minus 1 multiplied by 1 plus 0.1 z to the minus 1, which we can see here. The value that we're going to be substituting in for z to the minus 1 accordingly is when, for this factor of a, the denominator here being 1 minus z to the negative 1 is equal to 0. As of such, you'll get minus z to the negative 1 equal to negative 1, so that means z to the negative 1 is just going to be equal to 1. And once we substitute in that z to the negative 1 component here being equal to 1 for each one of these, we can solve for a as of such. The same method is going to be used for solving for b and c. Once we have solved for a, b, and c, you then check the Z-transform table to get the necessary Z-transforms to get this back from the Z domain into the discretized time domain. So we can see here that this denominator here being 1 minus z to the negative 1 maps to a transform of the unit step, being u of nt. And we can also see here that for our other factors here, being 1 minus 0.2 z to the negative 1 and 1 plus 0.1 z to the negative 1, this transfers to our a to the power of n u of nt Z transform as of such. So when you actually watch the Z transform table and perform these Z transforms, the final answer that you'll obtain for your closed form solution will be of this form here of y of nt, right, for this. Now there's one thing to note here in particular. Note that the Z transform here, for a of n u of nt, the denominator is 1 minus a z to the minus 1. So for this part here, this directly transforms accordingly. But because you have 1 plus 0.1 z to the negative 1, remember that this denominator can be expressed into the Z transform form if we extract this out as 1 minus 0.1 z to the negative 1. And this negative 0.1 here represents our a that's represented in the table transform accordingly. So that's why when you do the inverse Z transform, that's why we have that negative 0.1 here for the transform. Now, for homework, and this is actually for good practice, try to prove that for this f of z equation here, you can obtain the f of nt equation here accordingly for this. Alright, so this basically brings us to the end of the ECNG 2011 course for the entire semester. And unless we schedule any practice sessions and so forth, I'm letting you guys know Merry Christmas in advance, because that will be the last time I most likely am going to see you guys. So, are there any particular questions on the ZTransform material that we just now covered? Nice. I did finish marking your midterms. All I need to do right now is tabulate your grades before I can publish them on MindLearning. But I'm going to comment on that in a little bit because I need to talk about some of the common mistakes you guys made on the midterms, which you can avoid on the final exams. So I'm just looking to see if there are any questions regarding the ZTransform stuff before I move on to that. The marks were basically all over the place, so until I start tabulating, then I'll have a better idea. But there were some people that did really well. There were some people who did like average and so forth, and then there were some people that did horribly. So it looks like it might have been an even spread. It might be skewed more towards the higher side, but like I said, until I start tabulating the marks, I really won't be able to say for sure. Alright, so it doesn't really look like we have any questions on the ZTransform material. Alright, so things to comment on regarding while I was marking the midterm. And these were basically a few common mistakes that students made. The first thing that I noticed was that some people skipped steps, and that was something bad to do regarding the midterm because there was an instruction basically saying show all working in a nice and neat fashion that was printed on the front page of the midterm. So once you see that instruction, make sure you don't skip steps regarding your calculation and reasoning, because those steps actually do come towards marks in your questions. Yeah, try your best not to skip those steps. So a few people lost marks because they skipped steps deliberately when they were attempting some of the questions. So because of that, I could not award the marks, and as of such, their mark dropped a little bit as of such. However, because they had the correct answers going forward, they were still awarded marks for those. But like I continuously have kept on saying, your marks are awarded mostly on the approach that you take, not on the answers. So if you had a good approach but you got to the final answer, you still got a lot of marks regardless. The next thing I had to comment on was there were some people who wrote on both sides of the paper, where we gave you a specific instruction to write on one side of the paper, and thankfully, because it's me, I was able to make out the contents. But this is a general warning for you guys: try your best not to breach this instruction, because for some lecturers, once they see that you wrote on both sides of the papers, they can disregard your script for marking. Most of the times they don't, but if it's very horrible and they can't make out what you write, it's going to be to your detriment. So make sure you guys only write on one side of the paper when you're actually doing your exams. The final exam will follow the format of the previous years. Nothing is going to change about the format. So hopefully, I would say before the end of this week, I'll finish tabulating the grades on the midterm, and I can actually have those uploaded on the My Learning course shell for each one of you to see individually, because I don't want other people seeing other people's grades and so forth. So once you log in on My Learning, you will get your own grade. If you don't have access to My Learning, you can feel free to email me, and I will send you your grade via email, so that way you can see what you got. Alright, I think that's basically what I have to discuss in the midterm. So some general advice for the final exam. Like I said, your final exam is going to be 5 questions. Each question is going to be worth 20 marks, so that's a total of 100 marks. And your course breakdown, that's 80% of your final grade. The midterm was 20% of the final grade. So the general format that you're going to be watching in particular, you can watch the format for the last 4 to 5 years of past papers if you can get your hands on them. In particular, I think the Alma-Jova library online for the university has up to the year 2017 or 2018. But if you have any past papers coming up from 2015 go forward, you can basically see what the general format of the paper will be like for this year. Regarding the types of questions, what I can tell you is that what you were assessed on the midterm will not be assessed on the final exam. That has been a general trend for the last few years that the exam has been set. There was only 1 year that trend was broken, but the students were notified in advance that the trend was broken regarding this. So the content that you were evaluated on in the midterm, will not be evaluated on the final exam. And just to make things clear, that means down to the subtopics. So let's say, for instance, let's say if the midterm had a certain type of convolution, being that if it was just the visual convolution but not the mathematical convolution that was evaluated, that means the visual convolution will not come. However, the mathematical convolution could possibly come on the final exam. Similarly, let's say if the midterm had, I'm thinking of a good example here to give you guys. Let's say if the midterm had a certain type of assessment equation. Let me watch what my topics here so I can give you an idea what I'm talking about. Right, so let's say the midterm, for a good example, is our midterm evaluated initial and final value theorems. But however, we know that when you're evaluating initial and final value theorems, that also went in hand with pole zero plots. So because you didn't do pole zero plots in the midterm, there's a possibility that can come on the final exam while you're trying to do the initial and final value theorems in the final exam itself. So pay attention to what subtopics were tested on the midterm, because those subtopics will not come on the final exam in particular. The other piece of advice I can give you at this point, and this is what I said in the first lecture, is that you do need to practice. So practice questions from the final exams that are posted up, get the final exam past papers from the library website and practice those questions as well. If you see certain things in the past papers that I did not teach you, those will definitely not come, because like I said, I didn't teach you those material. Because those material were taught way in the past and the course has changed so much from then, those material will not be assessed. So once you see those certain types of questions in, let's say, probably like the 2010, 2011 past papers and so forth, you can ignore those contents because, like I said, I didn't teach you it, so it's not going to be evaluated. However, like I said a little bit before, if you can get your hands on the last 5 past papers for this course and you were able to attempt them and get a good understanding of how to go about the questions, you basically have a good preparation point at that pace as to how you can proceed with this year's final exam as of such. And you should do pretty well once you're able to do those questions. Finally, if you guys do require a practice session, I think, I'm not too sure if you guys got the exam timetable as yet, but if you do need to schedule any practice sessions, it needs to be before the week of the 14th of December. So if you do want to schedule any practice sessions, make sure it is before the week of the 14th of December. Because from there on out, I am going to be quite busy with administrative matters. Yes, if you do attempt any of the past papers and you're unsure about some of the answers, you can send me it and I can give you guys feedback by email regarding your attempts. But like I said, if it's a matter of attempting a specific year past paper or specific questions, and it's possible for you guys to schedule in a practice session where most of you guys can be online, I can do those questions for you guys online because I will have to schedule my time accordingly to make sure I'm here to do those sessions. Alright, so is there anything else you guys need to ask about the final exam or anything regarding the course in particular? Ask your questions now. The exam is basically open book format, so you can access all your content and whatnot to attempt your questions. Hopefully I should finish tabulating the midterm marks by Friday, for the latest. I should finish tabulating them a little bit earlier, if anything. They will be posted by the latest by Friday of this week. So they'll be posted on MyLearning, and once you log in on MyLearning, you can only see your grade you got on the course shell itself. If you don't have access to MyLearning, you can email me and I will email you your grade directly. No, I can tell you up front that this final exam is a full open book exam, so no content will be blocked from you. The final exam is 12 hours, so you have to make sure that you do the attempt in 12 hours and submit it back on the submission portal again. What I can tell you is I will not be in charge of executing the final exam. The examination sections of the University of the West Indies will be executing this exam. But the content that you're going to see on MyLearning is still going to be there regardless. It will not be blocked on my side unless exam sections blocked it. But like one of your classmates pointed out, just download all the content prematurely and have it offline for you to access, because like I said, the exam is open book. The YouTube videos that you see here as well will remain online indefinitely. I have no intention of taking down these videos until probably like if I'm going to run the next course, the next instance of the course next year, or if it's going to run during the summer, maybe Dr. Munir might use these videos. The exam basically is going to be like the same way how the midterm is, so you'll be given a PDF released at the start time, and you basically can, once you just download the PDF, it's just going to be the exam script. You attempt it by a paper, or actually, yeah, this is one thing you guys have to pay attention to. The final exam, you have to actually attempt this on paper and take snapshots of it. They will not accept digital writing or typewritten solutions. And that's also something to comment on regarding the midterm, because there was a specific instruction saying typewritten solutions will not be accepted because of the digital handwriting that was being accepted at the point in time. So if you, once you're doing this final exam, you have to actually write this on paper, and basically on one side of the paper while you're doing it, and take snapshots of it and upload those snapshots in a PDF form. They will not accept digital writing for your submission. And as much as we asked for it, they said no. So that's the only condition that you have for writing the exam. So yeah, once the exam released at the opening time, you're able to download the exam and attempt it, and then once you're finished attempting it and make your PDF, just upload it back, and that will be it. If there are any interruptions or anything regarding access to Myelin and so forth, examination sections will be handling all those queries and so forth, and they will accommodate you guys accordingly regarding this. So if anything that happens during the exam, remember, I cannot do anything regarding this. You will have to contact them, contact examination section, because they are the ones who are conducting the exam. I believe they are also making their own course shells for these exams, along with their own contact information and so forth in case anything does happen. So they can make accommodations to you while you're doing this exam. I also hope that all registration issues have been resolved, because if you're not registered before the exam begins, you will not be allowed to attempt the exam. And that is basically a university policy throughout all courses and all programs that are conducted by the university. Close this off for the time being. They are also very strict about their deadlines, so if you miss the deadline, they will not accept any submissions. So make sure that you do attempt the exam and you submit it way before the deadline. Right, any further questions? Alright, it doesn't seem like we have any further questions, so if there are any questions regarding the content of the ZTransform lecture or anything regarding the course itself, feel free to leave them down in the comments below, or you can directly email me and I'll respond to you guys accordingly. Just quickly recapping, if you do need to schedule any practice sessions, it needs to be before the 14th of December, because from the 14th of December onwards, I am going to be busy with administrative matters. So that's the date you have until to book your sessions accordingly if you need any practice sessions regarding this. If you're attempting any past papers and you're unsure about any sort of solutions, also feel free to email me. I can verify those solutions for you and give you guys feedback as to where you can go regarding solutions, if you're on the right path, if you're on the wrong path, and how to correct yourselves and so forth. Basically, that's it for the entire course. So, good luck on your final exam. Merry Christmas. Hope everything goes well for you guys this semester. And hopefully I will see you guys next year for a different course. So, until then, take care, be safe, and hopefully I will see you guys sometime next semester. Later.